Good morning, colleagues. Today we are going to solve exercise 3. From the book Fundamentals of Electrical Circuits. In this exercise I am asked to determine the zero current and the power dissipated by each resistor. By applying node analysis we know. First, what I'm going to do is mark the nodes. This one I'm going to call node B1, B2, C1, B3. The first thing I notice is that the resistors are in Siemens. Let's remember that this is conductance. The conductance G is equal to 1 over the resistance, that is, it is the inverse of the resistance. So, looking at this and remembering that the power is equal to B times I. P times I, but we could also find it as in terms of resistance as Y squared times R. And we could also find it as B squared in that resistance over R. So, if we want to do it in terms of Siemens and replacing this, what I am going to see is that the resistance is equal to 1 over the conductance. So if I replace this thing here, this equation is going to be I squared over R because it's 1 over what is Y squared over G. And what's here I'm going to put down here, it's going to be V squared times G. Yes, now I can to work with conductances. This is the way to determine the power or this other. Of course you could also determine the voltages and apply them. Okay, let's figure it out. Let's go look at that first. What I'm going to do is apply node in or apply to node B. I'm going to mark it here B1 and I'm going to look at the currents that enter equal to the currents that leave E. The first current I see is the one marked as sub-zero coming downwards. Okay. The other current that I see goes upwards, but here let's notice that there is a voltage source between the nodes and that is what we call the supernode. True? When there's a voltage source between the nodes it is called a supernova. This must be taken into account. What it means is that here it is a common node between B1 and B2. It's like here. Node B1 and node B2 were sharing the same wire. We'll see how. What does that mean? So what I have to do is look at the currents that enter and leave this entire point as if it were a common point. I'm going to mark the currents first to get an idea of the direction it has. I'm going to look at this power source. This current source is easier for me, but it reaches this point and here comes a 4 amp source. These two currents arrive here, therefore, I assume that the current will exit through here. It has to come out from one side and I say that's why. I'm not saying that it comes out up or down, because the current sources tell me that they are actually coming this way, not the current. This current that I marked here reaches this point. It has to take a direction to one side and what occurs to me is that it is going to come this way. Note that I am not marking the current direction in the voltage sources yet. Okay. Now what I'm going to do, name the current. I'm going to call this I1. I'm going to call it I2. So in the V1 node, well, in the supernode it is not a node. At this supernode or this point I'm going to look at what currents come in and what current goes out. First I'm going to put the ones that come out. The first one that comes out is the 2 amp one. The second current that comes out of this entire point is the current I sub 0 and sub 0, which has been this of this entire point, the other current that comes out of I1. the I1 yet. Remember that all this is a common point and those are the currents that come out of this node. That will be equal to the currents that enter from this side. Nothing enters from this side. This exit is the only one that enters current I2. Okay, now, starting from there, I'm going to rewrite the variables with equations for voltage and resistance and conductances, which in this case is conductance and the I sub 0, the I sub 0. We had said that it is good. If we went with resistance it would be voltage over resistance, but remember that resistance is 1 over conductance. This is the resistance. Therefore it would be voltage over a conductance. Obviously, doing the original thing we have to EHH, current is voltage times conductance. That has been the trend. So here the current I sub 0 is actually V1, which multiplies to 6 voltage times conductance in the current that goes down here plus the bad current, and current 1 is voltage 2 times the conductance of 5 plus voltage 2 times the conductance of 5 Siemens. That's going to be the current. This is 0. This is Y. Now it's equal to 42, but the current and 2 is V3 minus V2 is 3 minus V2. Yes, so if it were resistance it would be about, but since it is conductance it would be times 3. Well, here what I have to apply is something. Here it would be 2 plus 6 V1 plus plus 2 equals 3B3 minus 3B2. And now I continue to apply something. I'm going to leave the variables aside. I'm going to leave it here. It would be 6V1 plus 5 more 3 volts 2. If I'm going to the other side, and this also has 3V3 equal to minus 2. Well, I'm still operating. And I'm going to get that 6V1 plus 5V2 plus 3V2 would be 8 volts 2 minus. All of this is going to be equal to minus 2. That will be my first equation. I'm going to rewrite it up here to generate more spaces. It would be 6 volts 1 plus 8 V2 minus 3 V3 equals minus 2 in the first equation. Okay, now let's work with node number 3. Note that here, as we already did the analysis at this point, as a super node, we worked on node 1 and 2 at the same time. Now I'm going to work node 3 into node 3 into node 3. I'm going to look at the currents that come in. They're going to be the same. The currents that come out. Let's observe that there are two currents that enter, the one of 2 amperes and the one of 4 amperes, which is the one of 2 amperes, more than 4 amperes. That will be equal to the current that comes out, which is I2. Well, now this is going to be equal to 2 plus 4. That would be 6 amperes equal to current N2. The current N2 is going to be P3 minus P2, which multiplies the 3 axes. Yes, and Solving this, I'm going to get 6 amps. It's going to be equal to minus 3V2 plus 3V3. That would be our second equation. And save this, and I'm going to put it here. Note that since there is no variable V1, I am going to put 0 here. Then minus 3V2 comes plus 3V32 equals 6 amperes, and our equation number 2. Now the next problem we have is that there are 2 equations with 3 unknowns. There is no need for a third equation. Let's observe here. When we work with supernodes, do we have to do an LVK? Where is that node? It doesn't matter. Is it this way or this way? I'm going to do it for this one, which seems easier to me. Let's remember Kirchhoff. Now we know that the current enters from above, polarizes this resistance with more and less certain. The voltage here would be P1 plus and minus V. I'm going to replace this resistor with a voltage source that would be plus minus this would be V1. I'm going to do this like this later. We can do it in mind, and it comes here, and from this point I'm going to connect the voltage source. "10 volts is this one, that is this one that I'm going to find. This resistor will be replaced by a voltage source that I will call P2. I'm going to call it P2 more because we had already denoted it as the B2 voltage, and I'm going to end it here. And what did I do? I removed that resistor and replaced it with the voltage V1, which we had denoted mainly as the current coming downwards, since it is polarized more or less. On this side there would also be more minus the downward current, and I removed this resistor. I replaced it with a voltage source. True, nothing happens because the tension will not change. If I already have it, then what I am going to do here is not going to change now, and I am going to obtain that here would be less voltage P1 plus the 10 volts plus the voltage V2 can equal 0. Voltage 1 plus voltage 2 equals minus 10. This would be our third equation. I'm going to delete this. It would be less V1 plus V2 plus 0 equals minus 10. That would be number 3. Well, we now have 3 equations with 3 unknowns. Well, what follows is to solve this equation. I'm going to use MATLAB. This type of exercise, it is convenient to use a calculator that can be done, or a program, or any Jordan method and equalization, substitution, reduction, as you want. When they are real exercises, it is more convenient to use something like MATLAB. So I'm going to solve it with MATLAB. Here it would be 6, 8 and minus 3. Here it would be, I'm going to delete this. Here and here I already had it, 6, 8 minus 3. The next one would be 0 minus 3, 3. 0 minus 3, 3, and the other one would be minus 1, 1 and 0 minus 1. 1 and 0. For matrix B it would be minus 2, 6, 10, 2, semicolon 6, semicolon and minus 10. Well, notice that here it would be 6 space 8 space minus 3 for the first row, as it would be 0 space minus 3 space minus 3 for the second row, and minus 1 space 1 space 0 for the second row. Then I'm going to run the program and observe the results. Well, here they give me the voltages. Here it tells me that the voltage V1 is equal to 4.9091. The voltage V1 equals 4.9090 and the voltage V2 and the voltage V3. V2 minus 50909. 5.0909. It could show two significant figures, but well, and the last one would be minus 30909. 30,909. Well, now what the exercise asks us to do is determine the powers consumed by each resistor. Well, I already have the voltage. This equation deletes it. I no longer need it, but you can rewind the video, and I will determine the powers at those points. The first power that I am going to finish, this resistance that is in terms of semis of the power, the 6 is going to be equal to what we had said. That's what we're going to use now. Well, if we have voltages, we can use this equation. This one here. So it would be the voltage squared. The voltage would be the voltage at point 1. C would be 4.9091. The square is multiplied by 6. That gives me 144.59. The power in the next resistor, which would be the 5, that would be the voltage 2, which is minus 5.0909 squared times 5 is 129.58. Watts. And in the resistance 3S, we know that, well, we could do it in two ways: by finding the current or doing it with voltage. Let's do it both ways. We could do it in the following way: determine the current and the current too. Remember that we had already said that it would be B3 minus B2. B3 would be minus 3.090909 minus B2, and B2 negative 1 would be plus 5.0909. This gives me good B3 minus B2 about, well, it's not about, it's about. For 3S, for 3, this is here. It's the current, right? We can square that current and multiply it by the conductance, which would be 3. That way we can find the power at that point. True, because all of this, let's remember, all of this that is here is common, and that current, it is the current that passes through I2 B2 minus B3 minus B2 times the conductance 3. It gives me the current. I read the current squared, and I have to divide it, not multiply it. Well, let's remember that we are working with Siemens. In reality, it would be dividing it when it is with resistors if it would be multiplying. But here, as it is with inductance, we have that it is divided into 3 of this. In this way we can determine the power. Well, I'm going to delete this. I'm going to put it right. I've already divided all this whole expression divided into 3. The other way would be in terms of voltage. What would it be like in terms of voltage? Oh, okay. And I already have the voltage here. I already have the voltage here. I already have the voltage at those 2 points. I can simply say that voltage 3 and voltage 3, it would be -3 -3 minus voltage 2 would be more or less here 0909. This, if I multiply it by the conductance is 3 due to the conductance of the current. And if I divide it by the same conductance, it will give me the voltage. Then the voltage would simply be what it is. That's B3. B2 is going to give me the voltage on that resistor. And I just square it. I square it and multiply it by the conductance. In this case it would be 3. This would be the other way, as this would be the A3S voltage. And I square it, multiply it by the conductance, it gives me the power, and that power would be 12 volts. Please, if you want, I will verify this one and these will be exactly the same. Ready, mates? So this is where the exercise ends. See you in the next one.